Hi again everyone, Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my live streams of mathematics videos, and I'm going to show you how to compute the value of an infinite series. I'm going to step you through an example and show you how it all works. So let me share my screen with you and we can get down to business. Okay, so this is the series that we're dealing with. You've got the sigma notation here. N is the dummy variable. So essentially this is just an infinite number of things added together where the thing that we're adding depends on this. Okay, now you might want to think, well, ask, why is that an interesting problem? Well, series are everywhere in mathematics. You might have heard of geometric series, or Fourier series, or power series. These series occur frequently in engineering, in physics, and applied mathematics. Now, the example I'm showing you here today is a very basic series of constants, but it's kind of interesting to consider what happens when we're adding an infinite number of things together. So let's get back to the problem. Okay. Now, firstly, this is an infinite sum here. So the first question is this whole thing well defined? Is it finite? Is it infinite? Or how can we work this out? Now, in this particular example, we're asked to compute the value of this. So that sort of gives us a hint that this is actually finite and of course computable. Okay, so let me step you through it. This kind of series is a telescoping series. Okay, so let me just write that down. A telescoping series or a telescoping sum. All right, maybe sum is a better word here. But what happens is when we write out the first, say, big N terms of our series or our sum, you get a lot of cancellation going on. So let me just repeat that. In a telescoping sum or a telescoping series, if you write out the first, say, big N terms, you'll get a lot of cancellation. And in this case, you're going to be left with only two terms, if you like. Okay, so let's see how that works. It's just basically an algebraic manipulation. Okay, so the secret here is to work with the summand, the thing that we're summing. Okay, so let's do that. Now, I can write this as the following. I can use partial fractions to split that up into the following. And you can do partial fractions a number of ways. I've got lots of videos on that. You can use the Heaviside cover-up method, the method of undetermined coefficients, or you can just do it very quickly and say, all right, I've got a 1 there and a 1 there. Let's add n, so I have an n there, and take n away. Okay. Yes, and take n away. Now, if I split that up into two parts, this will cancel with this will cancel with this, so I get the following. Okay, now let's put this into here and write out, say, the first nth, big nth partial sum. Okay, so let me just define this in the following way. So S sub big N is defined to be the following. So instead of having an infinity sign up here, I just have a big N. So it's like the big nth partial sum. This is what we're talking about. All right, so this is just, let's replace the summand with this difference. Okay, and now you might think, well, hang on, what's going on here? Well, this is the part of this solution where the magic happens and all the cancellation occurs. Okay, so what we're going to do is we're going to write out some of the terms associated with this series now. So let me show you. Okay, so let's write this out. So for n equals 1, I'm going to get 1 minus a half. Okay, this is for little n equals 1. And then if I move on to n equals 2, I'll get a half minus a third. Add that in. Okay, and let's continue. I put in, say, n equals 3. I'll get a third minus a quarter. Okay, and you can continue that on. So the plus dot 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 means I'm going to come up to the big nth sort of term now. So I replace little n with big N. All right, so let's see what happens now. Well, you can see this negative a half is going to cancel with this positive a half. This negative 1/3 is going to cancel with the positive a third. This negative 1/4 is going to cancel with the positive a quarter in the next bracket. And similarly, this term will cancel with the previous bracket. So what am I left with? I'm left with 1 minus 1 on big N plus 1. Now, why are we writing out the big nth partial sum here? Well, this thing here is just the limit as big N goes to 0. So to go from here to here, basically you just take the limit as big N approaches 0. So what we can do is just take the limit as big N approaches 0, work this out, and we've got the value, the value for this boxed infinite series. Okay, so let's do that. So if I take the limit as big N approaches infinity, this will go to 0 and this will just stay 1 as 1. Okay, so let's call this star. Okay, star converges to 1. Okay, so let's just recap what we did there. First of all, we looked at our summand and we realized that we could write it as the sum or the difference of some other functions using the partial fractions technique or partial fraction decomposition. Then we wrote out the nth partial sum, the big nth partial sum, and we saw some beautiful cancellation. And this is the characteristic of these so-called telescoping sums or telescoping series. We took the limit as big N approaches infinity, the limit of our partial sum, and that gave us not only the information that the series was finite and converged to something, but we got the value that it actually converged to, 1. Okay, now that's very, very rare in the theory of series. It's rare to be able to explicitly calculate the value of a series of constants. Usually we're just interested in whether a series converges, whether the limit involved exists, or whether it diverges, where the limit doesn't exist or it goes off to positive or negative infinity. Okay, so let's just go through that one more time. Let me share my screen with you. All right, we were given this telescoping series. We then used partial fractions to write it like as a difference, if you like. We wrote out the nth partial sum, and we saw this beautiful cancellation, then took the limit. And we concluded that the original series converges to 1. Okay, so where does the name telescoping come from? Well, this is, I don't know, this is a bit like a telescope. You can expand it, and then all these things cancel, so you can compress your telescope down as if you're putting it in your pocket again. That's my theory anyway. I don't know if that's correct. Okay, hope you enjoyed this presentation. In forthcoming videos, I'll talk more about series and certain tests involving series for the convergence or divergence of those series. Hope you can join me for those presentations. If you have any questions or comments or suggestions, I'd love to hear them. Put them in the comments section below. Thanks for watching, everyone. See you soon. Bye.